Okay, students. So today we are going to do a quick study session, but detailed, in-depth, quick study session for ring laser gyro. In order to understand what ring laser gyro is, a topic that I have seen intimidate students a long time from all places. Okay. In order to understand ring laser gyro, we'll be looking at what laser stands for. It's an abbreviation. Okay. And we'll see what is the function of ring laser gyro. To understand ring laser gyro, we need to first know where it is used. Now, ring laser gyro, as it is often called, is used in inertial reference system. In the inertial reference system, there is an inertial reference unit. The reference unit has ring laser gyro. As any gyro, even this gyro performs the same function. What is the function? It will have rigidity, and rigidity will help us with some reference. With respect to the type of gyro instrument used, we can get a reference with respect to rate gyros, that is rate of turn indicator, turn coordinator. And then we have attitude indicators that measure roll and pitch angles from a stable horizontal. And then we have directional gyros that give us direction with respect to a stable north. With respect to ring laser gyro, this gyro is used in inertial reference system to provide a stable platform. A stable platform is required for inertial reference system to give us the data that inertial reference system gives. Now, what is this data? The data is very important with respect to many important elements of the aircraft flight parameters. But before we go to inertial reference systems, we need to know what these inertial systems are. So it all started with Inertial Navigation System, INS. Now, Inertial Navigation System simply means a self-contained system that is independent of any external input. It means it is a system that has its own data derived by its own self with respect to aircraft parameters. No external input is required. So this gives us a self-contained independent system used for checking and noting navigation parameters so that we can use it for autopilots, for flight director systems, and for manual flying as well. Now, INS was the one of its kind first self-contained navigation systems. INS has 3 or 4 components. We have accelerometers, we have gyros, we have computers, and then we again have computers. Now, accelerometers, they are the main primary sensors in any inertial system or inertial navigation system. When I say primary, it means that the main element that actually gives me my inertial navigation based data. Okay. That in itself is the accelerometer. Now, how does this accelerometer work? The accelerometer is considered to be a pendulous device. And whenever the aircraft is accelerating ahead or it's slowing down, the pendulum swings ahead or behind. Based upon the movement of the pendulum, electrical currents are picked up, and the amount of the electric current is sent to the computer, where the computer analyzes the amount of current and amount of pendulous with respect to the amount of pendulous movement with respect to the accelerometers, and it gives us time. With respect to time, we then use data from the accelerometer to give us velocity. And it is all based upon the sensitive movements of the accelerometers. What is the displacement from their initial fixed position with respect to going up, going ahead, or going down? So, in order to get acceleration linear forward, south, north, south, we have one accelerometer going north, south. And then to check lateral acceleration or east west acceleration, we have another accelerometer. So together, whenever aircraft is moving forward or slowing down or turning left or turning right, these accelerometers will sense the difference in the movement of the pendulous device inside them, and little current variations will be fed to the computer, and the computer will give us the related data output. Now, what are the kind of data output that we can get from an INS? So the INS first will sense time with respect to the accelerometer. So there are the computers that will integrate accelerometer with time, and then I will have another computer that will integrate time with velocity, and then together time and velocity will give me my distance. Now you might be wondering what is happening. Now this distance that I will measure will also give me my position elements as to where am I with respect to my previously known position. Now, all of a sudden, INS is something that we have spoken about with respect to key elements. Okay, there's an accelerometer, there is a computer, there are two computers. Accelerometer will first sense time, add it to the computer. Then, based upon that function, it will give us velocity, and based upon time and velocity, it will give us distance. INS requires only one data from the outside. Earlier, we said it's self-contained. It is self-contained, but one reference we need to give, and that initial reference is the aircraft's position before departure. And that position has to be fed into the computer by the pilot manually. So the computer system associated with INS would be computer display unit. CDU, it will be just like how a calculator looks. I'll show you pictures from Oxford books right now. Okay. So in the INS, you can feed in the present position accurately. Then that position is the reference position with which the INS will sense all its other data. So the accelerometer will sense their deviations from the present position, calculating time and velocity, and of course the direction. And when they figure out that, okay, we have flown for this time at this velocity from this position, the computers can help determine the present latitude, longitude position of the aircraft, automatic by itself. So that is the function of INS. Such information is widely used in all our wide body and glass cockpit aircrafts. So the things that you see in videos where pilots are seen inputting some data on some computer on screen, so they are inputting or they're feeding in the present position for the INS system. And then they're also feeding in waypoints, which is an advanced function. If you can feed in the waypoint lat longs, and if you can feed it the destination and the departure, then the INS in itself will determine whether the aircraft has gone off track. If yes, then what's the track error angle? If the aircraft has gone cross track, if yes, then what's the cross track angle, error angle, cross track error angle? Then what's the present position of the aircraft? What is the heading of the aircraft? What is the drift angle of the aircraft? What is the ground speed of the aircraft? What is the track of the aircraft? What is the distance and time? And what are the steering capacities of the aircraft? So if you see, my INS with respect to accelerometers will give me nav data, and it will also give me aircraft attitude data. In nav data, I have aircraft position. The only thing, make sure that we have to feed in first is the aircraft present position at the time of which the aircraft should be fixed, and it will be aligned with the true north. Then we have cross track error. Then we have track angle, track error angle. So this is cross track error. This is track error angle. And Then we have, what do we say, heading displayed. We have drift angle displayed. Then we have ground speed. We have track. Then we have distance. We have time. And then we have steering also. In what direction are we steering? Right, left. All this information is available with the help of INS. Now, this INS in itself is a system. Inside the INS, the sensor system is known as inertial sensor system. Inertial sensor system will have those accelerometers and computers. Now, I said there could be two type of accelerometers, north, south, east, west. Sometimes to measure vertical acceleration, that is rate of climb, rate of descent, we can have a vertical accelerometer as well. So in total, there could be three accelerometers in any inertial reference correction, inertial sensor system, which is the sensor unit of inertial navigation system. The navigation system or INS will have the sensor unit, will have the control panel also, right? The whole system will have it. While the sensor unit will only have the accelerometers and the computers. They are the sensors. So the input and output, input and visible screen will be the CDU, computer display unit. Okay. Control and display unit, we call it generally. So we control things from this and we also get display of the information. So not computer display unit, it's just control and display unit. I'll be showing you pictures right now. When it comes to attitude data, okay, whether there is pitching, rolling, then we get the following information from an INS. We get roll, how much is the aircraft rolling? We get pitch, what is the pitch moment of the aircraft? And we also get the heading. Now the heading is of the platform. Now what is this platform? You will come across the term platform. Now this platform can be considered as a horizontal plate on which the accelerometers are mounted. But the problem is the platform is unable to stay horizontal when the aircraft is maneuvering. In order to keep the platform horizontal, we can use gyroscopes. So we call them integrating gyroscopes. Now that is the function of gyroscopes in INS, to keep the platform horizontal. So generally we can have one gyro, but we have in total 3 gyroscopes aligned with all 3 axes of the aircraft. Together, they give us a stable platform. So the importance of gyro in INS to give a stable platform, while the accelerometers on the stable platform will help us with all the data. So gyros are not helping us in any other thing apart from giving us a stable platform. But in an INS, which is an older system, we don't use ring laser gyros to give us a steady platform. We use a different kind of gyro, and that is termed as we can say it's a gyro, a mechanical gyro, which has a viscous fluid instead of springs. Now, what kind of gyro has springs? If you remember turn and slip indicator, a rate gyro has springs. A rate gyro has spring to make sure it comes back to its stable position. Your integrating gyroscopes in INS are rate gyros. A very important point, very common point. And these rate gyros are single degree or 1 degree of freedom gyros. So now in an INS, which is the older version, we have 3 accelerometers. Mainly 2 are enough, but 3 vertical acceleration based accelerometer can also be used. And then we have mechanical gyros, which have viscous fluid instead of spring, single degree of freedom. Rate gyros are the gyros. So we have 3 gyros, which will stabilize the platform, while we'll have accelerometers on the platform, which will give us all the data as mentioned here on the screen. And then we'll have computers that will feed the data and convert the data into the requisite information that we need. And then through the control and display unit, we'll be able to, select what function we want to check and feed in the data and check information. Then, of course, the navigation display of the aircraft will give you related information. So this is how you directly get true heading, true directions of the instrument and you can not totally depend upon your magnetic compass or remote reading compass or other compasses, because then your aircraft has INS, you are getting adequate information. So I would suggest you all go through the notes once this session is over, as this is just a quick session. Understanding is very difficult. It's very difficult to understand from the text what's happening. So I'm making it easy for you. And I want you to make sure that after you attend this session, you quickly go through the notes and then just go through the solved questions. Okay. So I'll show you pictures and explain then the same thing again. It will make much more sense to you. Now, the problem with INS is that it is mechanical and it takes extra time to be stabilized. Remember, every gyro needs to develop that rigidity, so it needs time to stabilize. Plus, there are a few more errors. Now, in order to advance the system, INS was modified into IRS, Inertial Reference System. The sensing unit was called Inertial Reference Unit. Inside the Inertial Reference Unit, I have 3 accelerometers. Of course, I have platform, I have computers, and I have ring laser gyro. This ring laser gyro is a very advanced version of gyro where it uses light to determine or to give me the benefit of a single degree rate gyro. In short, it gives me a stable platform. So a little bit of understanding about functioning of the what do we say? RLG is enough. Rate correction. Ring laser gyro is enough for us to understand. You need to know what is happening and why it is used. The RLG is just used to give us a stable platform again in IRS. Why IRS? Because IRS, because it uses ring laser gyro, it is free from most of the errors and it has the following advantages. Now, what are the advantages of IRS? Simple, I'll just quickly tell you the advantages of IRS and why we use IRS. The control and display unit will be the same. I'll be showing you pictures right now. So the advantages of IRS. Why IRS advantages? Because RLG, ring laser gyro, is a part of IRS. So the advantages of IRS are single activation, like the time taken to activate the system, it is almost zero. We have 1 second activation of gyro. So it's quick to use. Okay. What gyro? The gyro is the rate sensor. Attach the keywords rate sensor with ring laser gyro, a single degree freedom gyro. Okay. Second benefit is maneuvering. Whenever the aircraft is maneuvering, pitching up or rolling, the effect of gravity, which could give me wrong indication, okay, the effect of gravity is not impacting my IRS. So it is insensitive to the G attitude, we could say. So in maneuvering, you could say my IRS is insensitive to G attitude when the aircraft is like going down the acceleration, and it is also insensitive to rolling and pitching. So rolling, pitching, and falling vertically up or down will not give me any errors because the platform would be super stable. Okay. Construction. Construction is simple. Mechanical construction is very simple and it is highly reliable. And then range, we have wide dynamic range, we can say. These are key points that can come in the exams. And then we have drift. We have very small drifts. Now, drift with respect to gyro can also be said. Small drift rates. And the only error that can be induced in an IRS would be operator-based error when the operator, as in the pilot or the person operating, feeds in wrong data. Okay. Now, in IRS, mainly you have to focus on the advantages, the benefits, and how the RLG works, that is ring laser gyro. So let me share screen with respect to the textbook, making it easy, and I'll just quickly explain the INS, a little bit advantages, walk you through the text to know what to read quickly. And then we will quickly see the ring laser gyro. And I'll explain how it works in short, follow the diagram with respect to what I show on the screen and look at the key points and just quickly go through the text and make your rough important notes. There would be important things. I'll just highlight those things because it's a quick session. So make sure you're trying to grasp it. Okay. And remember, we're just using using the text for our personal reference. So please, anyway. So see, this is inertial navigation system based. So this is how the platform looks like. Okay. And the aircraft you can see is aligned like this. In the platform, these are the accelerometers. Now, this is one gimbal or gimbal we can say. And remember, if they ask whether the gyro and the accelerometers are in the same gimbal or different gimbal, we'll see they both are in the common gimbal only. We'll see. Nav data, altitude data, as it is obtained. Altitude data can directly be derived, but everywhere computer will be giving me information with respect to time, velocity, and all this information. Attitude data could be taken directly also, all right, with respect to the rate gyro features. But we have the accelerometers giving us all this information. So this point, pitch and roll attitude is also available when we have the time and the velocity being calculated. So this line is very important. The purpose of computer is to integrate the accelerometer output with time to give velocity, and then integrate velocity with time to give distance traveled. So the accelerometer will measure the time differences because of the pendulous effect, and the computer will measure that time to give us velocity. And that velocity, again, going through a computer will give me data, which will be pitch and roll attitude data, true heading, true track, drift, present position in lat and longitude, present position, ground speed and wind. Okay. From the sensor, inertial sensor system, the information is sent to the navigation system using another computer, where we can actually store in waypoints also, and we can get track error angle, distance and time to go and to reach them. So everything is available with the pilot with the self-contained system. In the system where I need gyros to stabilize the platform, accelerometers on the stable platform, and computers to do the calculations. This is an INS. This does not imply it does not imply rate ring laser gyros. It has gyros with viscous fluid. We'll see the picture. The primary measuring device for INS is the accelerometer. Remember? Okay. And the accelerometer is basically a pendulous device. The acceleration measuring devices, the accelerometers, they sense any change in the aircraft velocity, either as an acceleration or a deceleration, very accurately. Now, there will be two type of accelerators, one in the north-south direction and one in the east-west direction. The first is in the north-south, second is east-west. A third accelerometer can be used, which is fitted to measure vertical acceleration. Okay. Now we can skip all this. We can do it for ATPL. What is an integrator if they talk? Amplifier integrators, they're just to increase the amount of current measured. See, this is how the platform looks like. A gimbal is there. Okay. There are two gimbals, pitch gimbal, roll gimbal, but the platform and accelerometers are in the common gimbal, the pitch gimbal we can see here. Okay. These three cylinders are three gyros. One is tilt sensing gyro, one is azimuth gyro, and one is east-west tilt sensing gyro. So one will be north-south tilt sensing gyro, one will be east-west tilt sensing gyro, one will be azimuth gyro. And then there will be two accelerometers. One will be east-west accelerometer, north-south accelerometer, and there will be one more vertical accelerometer. It's not mentioned in this diagram, but it will be in other diagrams. So this is the platform. Gyros are to stabilize the platform. If you don't stabilize the platform, then the INS will be impacted by the gravity effect. We don't want the INS to be impacted by gravity effect. So we make gyros to keep the platform stable. The computer associated with inertial navigation system, it will know the latitude and longitude of the takeoff point, how the operator will input it, and calculates that the aircraft has traveled so far in the north and so far in the east-west, and it based upon time and speed, it determines where it has calculated from the present position. So make sure your present position is accurately fed. And then the departure position, and then based upon the departure position, it gives us our present position in lat and long also. The new position can be given to us in the tenths of minute, rounded off to the tenths of minute. D long, degrees, minutes, seconds, up to tenths of minute. Now this is a control and display unit, a common control and display unit, where present position is shown. How? Now let me show you. This here, the radial button shows you the different functions you can select to observe. So you can select position function, you can select waypoints, distance, time, wind, track, test, track, ground speed, heading, drift angle, cross track error angle. Desired track, this is desired track. So this rotary knob will give us different functions. Okay. Then we can insert using this button whatever data we feed. A little bit of alert, battery, warning, indicators, track, change. This is a rotary knob to dim or brighten the displays. Waypoints can be selected from here. And here displays of positions are given to you. Okay. So using the velocity and present position, it can solve a lot of things. Now remember the gravity effect. Because of the gravity, the basic INS, basic accelerometers will have errors in pitch and roll planes. Because of that, we use gyro so that we can keep the platform stable. So the importance of gyros in an INS to reduce the gravity effects, which would impact in the pitch and roll planes of the aircraft. Now, this is that integrating gyroscope. Is a 1 degree freedom gyro, which uses a viscous liquid. The liquid is here in this metallic frame instead of mechanical spring. So it's a single degree rate gyro called the integrating gyro. So see here, the rotor is there, rotor axis is there, and it is pivoted properly, and then it is put into a frame, which a frame and a cylinder, which has viscous fluid instead of spring to keep it stable. So these are just key points you need to remember. This is not an RLG because RLG is an IRS and this integrating gyroscope is in INS. INS is older, IRS is new one. Now this is again a platform to keep the platform stable. We have rate gyros. See, 3 gyros, 3 different axes, and we have 3 accelerometers, north, south, east, west, and vertical accelerometer. So that is the platform. Accelerometers will give me time and velocity based upon which I'll have all the nav data and roll data, while gyros will give me a stable platform. Okay, simple. See, the gyro and accelerometer are mounted on the same gimbal. 3 integrating gyros are mounted on the inertial platform with their input axis mutually perpendicular. So remember this, there are 3 gyros. Rest, you can skip reading if you want. You can read a little bit. Remember the earth rate. 15.04 apparent wander over there. And if somebody asks how is earth rate and transport rate compensated, you say by torquing the gyro. Using a torque motor, we compensate for it. Coriolis effect, centrifugal effects, like we have seen in basic gyro. Platform rotation can cause the local earth to maintain the local earth vertical here. Coriolis acceleration caused by the aircraft following a curved path in space. So just definitions are given to you. You can make a note of it right now. Warm up period up to 4 minutes, 3 to 4 minutes. Course alignment. So this is how the starting period is, which is the drawback. Okay, where IRS and uh, the ring laser gyro give us benefits. Remember, platform must be aligned with true north. Okay, all accelerometers must be level. So it's just basic. Now, what is the Schuler period? Now, the Schuler period is with respect to a scientist named Schuler. Forgive me for the pronunciation. And they have said that if we make a pendulum with its string equal to the Earth's radius. So see, a pendulum equal to the Earth's radius. And if it is swinging, then the period of the swing would be 84.4 minutes. So the Schuler period can come in question. The answer is 84.4 minutes. This effect can impact the movement of aircraft on Earth when it's traveling over the surface, because an aircraft, as it travels from surface to surface, it can behave as a pendulum as well. So Schuler period 84.4 minutes, and it is required to maintain the platform horizontal because of this impact, which we are able to maintain. If it would not be stable, then we would know that the platform would oscillate within a period of 84.4 minutes, which is known as Schuler period. But we have a stable platform because of gyros. So this is just an explanation as to why otherwise we also need stability in our gyro in short. Remember Schuler period? Schuler was a scientist. In that, the pendulum has a length equal to the radius of the Earth. Bob is from where it is held, and the point of suspension, the Earth's surface. You can read for the errors, it's fine if you don't read. And then whenever you get time in future, you can just go through this. Anyway, you'll be learning this in your type rating and for your ATPL exams, how to operate the control and display unit for an INS. Okay. You can go through the INS warning lights for exams. If you have a green light, it indicates alignment complete. And if you get this indication, and if you get a green light, so you have to select nav. Battery related warning light, you will get a red light, indicates battery power is too low. Check your battery power supplies. Alert, you will get an amber light indicating you are approaching a waypoint. And unless you are in manual mode, you don't have to do anything. So here you can keep it after you have read through the control and display functions from the paragraph. What will be more important with respect to exams right now would be RLG and the differences. So chances are they might not be expecting you to get into detail functioning of this because these are not available on training aircrafts. So your CPL will be on a smaller flight and you will not have these systems, but basic understanding can be asked. So just make sure you have read through these basic solve questions here, just in case on a safer side. Okay, I've marked it correctly from this. And just keep a mental note of it just for the sake of exams. Now let's come to IRS. Now the difference in IRS is the type of gyro used. So the ring laser gyro. So this is how the IRS looks like. And this device here inside, although in your diagrams it looks like RLG is uh, small like a box of chocolate shaped thing, but it's quite huge. It's like almost a square, a cube. It is triangle. It has a ring. We'll talk about it. When we say strap down inertial navigation, it means it is self-contained and you can just attach it to the aircraft and start using it. It's like a line replaceable unit. You can always take it and replace it and go. It is that easy to handle. It has computers, microprocessors. The difference between the integrating gyroscope of INS and ring laser gyro of IRS is that the stable platform is achieved not mechanically but through mathematical calculations. So the data from the ring laser gyro when the aircraft is moving will be sent to certain computers, microprocessors, and then mathematically corrections will be made where platform stability would be derived mathematically. So that is the advantage. What are the different outputs that you get similar to INS, where we had inertial reference system? In IRS, we have inertial reference unit, which gives us all this information. So much information is available. Pitch and roll, heading true and magnetic, accelerations, angular rates, even yaw rate is observed. Inertial velocity. Inertial means self-contained. Okay. You don't need any output data. Position can be obtained. Wind data can be obtained. Imagine wind data is obtained. And what all calculated data. Apart from all these things, the rest of the data is this that can be calculated. Now, who uses this information? All these systems use this information. You'll be surprised to see your VSI, your HSI, your attitude direction indicator, they are all using this data from INS to compare whether they are sensing the right thing or not. The primary source of the IRU, it's its own sensors. What are those sensors? The accelerometers. There are 3 gyros, 3 ring laser gyros, and 3 inertial accelerometers. So the gyros and the accelerometers are primary source of information in your IRS. Okay. Other inputs that you need are initial position, operator fed, barometric altitude. It will know the altitude also and the TAS. So remember for IRS, you'll need these 3 information initially to be fed into the system. Note that initial position will be required because whatever your present position would be, it would calculated based upon the time and speed from that position to the new position. Altitude will stabilize the vertical navigation and thereby stabilize the vertical velocity and inertial altitude outputs. So this is the importance of having barometric altitude initially. It will stabilize the vertical navigation. And the task input initially that we will give to the system will allow the reference unit to calculate wind speed and direction. So 3 important points based upon the secondary source of information or external sources of information. So primary sources are 3 gyros and 3 inertial accelerometers. And the external sources we could say or only other inputs are these 3. And the individual functions are also mentioned. Make a note of it. Let's quickly jump to laser gyro. I don't want to stretch out the session time too far. Laser stands for, okay, so there is a, what do we say, uh, abbreviation of laser, okay. We'll be going through it. But what is the main function of laser gyro? The laser gyro is a gyro that uses the characteristics of light to measure motion. Remember, the rate gyro also measures motions, gives us rate of turn indicator. These gyros are rate gyros. There is an effect called a Sagnac effect. Okay. What is the principle? It will be very easy when I show you through the diagram. But look at the full form of laser: light amplification, LA, and simulated S, emission of radiation. Laser is light amplification and stimulated emission of radiation. Okay. So RLG, ring laser gyros, they measure rotation by comparing two laser beams which are opposite in direction in a very narrow tunnel. Okay. A lot of keywords are there, how laser is generated. But let me quickly come to the construction aspect. So this is a narrow tunnel. You see this, and this completes a ring. This is why it's called a ring gyro. There is a cathode and there are anodes. This cathode will be shooting electrons. The required frequency will be reflected by mirrors. There are 2 to 3 mirrors. Generally, there are two main mirrors and one prism, total 3 mirrors. What happens is the electric signals are sent at the same frequency on both sides, from this side also, from this side also, from the cathode. So these two anodes are attracting the electrons on both sides. Cathode will send electrons, they will attract electrons. Now here there is a mirror, here there is a mirror, two main reflecting mirrors. They will reflect the required frequency and absorb the unrequired frequency. And what happens is, whenever the platform is stable, okay, whenever the movement of the aircraft is stable, the time taken for the light waves will be the same and there will be no difference. Anytime when a movement is observed, the difference will exist between the light rays going in one direction and another direction, and the difference will be studied at the point of interference here. So here what happens, there are detectors. Photocell detector means light detectors. Here, because of helium and neon gas used, the electric currents are converted into light, and that light is further then reflected to go through the mirrors and then reach these detectors. These detectors and the prism together measure the interference of the two beams. And whenever there is no difference, no moment is registered, or whenever there is movement, a difference is registered. And that difference gives us a fringe pattern. And that difference, when calculated, will determine the difference in the frequency and the difference in the wavelength. And that little bit of difference will be fed to the computer, and the computer will give us mathematical stabilization of the gyro. In simple words, this is more than enough for us to understand. Once you read through the highlighted text again and again, you will understand it more. But this is more than enough for us to understand what is happening. We are using two light rays, which, when there is no motion, will not have any time difference at the interference point. But whenever there is motion, there will be difference in one and the other traveling. There will be difference in their velocity or the time reached that will impact their wavelength. Small differences will be mathematically calculated, and a mathematical horizontal platform will be created for my sensors with respect to internal calculations. Now remember, the laser gyro used in IRS is an angular rate sensor, a rate gyro. Okay. All the light rays travel at the speed of light. Now, whenever the movement is experienced by the gyro unit, and that would cause the two signals to vary from each other, there will be a frequency change in the two currents going in both the different directions. And this effect, the change in frequency, because there is a change in the path length due to rotation of gyro. So we understand, whenever the gyro is moving, whenever the aircraft is moving, the length taken by this black or blue arrow and the length taken by this red arrow will vary because of the movement. And because of the length varied, because the light is traveling at the speed of light, the frequency will vary. Some frequency will decrease, one will increase. So the change in frequency because of the change in length due to the rotation of gyro is known as Sagnac effect. Why is the length changing? The length required for them to travel because of the moment. Whenever we have movement away from the horizontal, both the rays traveling will have a difference in their length, because of which the length traveled in the tunnel, because of which frequency will change, and the change in frequency will be measured. This effect is known as Sagnac effect. Now, the mirrors that are involved are not identical. One mirror will make micro adjustments. Okay. Other is partially transparent. So one will make good adjustments. Second will tra- reflect the required frequency and absorb the ones that are not required. Another is partially transparent to allow the laser light to be detected on the photocell detectors. So one mirror is to make micro adjustments to keep the physical light path accurately aligned, and another is partially transparent. Why? To allow the laser light to be detected on the photocell detectors. Where is the photocell detector? Here is the photocell detector. So these are the two light beams. The dither motor is a very simple thing. This motor is used to prevent a lock in RLG. RLG has a drawback that it also has a lock similar to gimbal lock when rotation speeds are very less. So we use a dither motor. A dither motor will create a mechanical torque over there, an electronic torque, and it will help us with that lock. Now in the second mirror, so this is the second mirror they can say, okay, this here. So these are two mirrors, but this is the partially transparent mirror which will allow for the light waves to be sensed by the photocell. We need these photocell indicators for the completion of our ring laser effect. You see this one going to the prism is coming back here. So the length is varying here also because of the prism. Included with the second mirror is prism, which flips or redirects the light beam around, causing it to meet and interfere with the light beam that is directly aimed at the photocell. So they can ask you the meaning of prism. So one signal is going directly to photocell. Second is going to the prism and being reflected back here at this point. This reflection is important for me to understand the differences. Okay. The beams alternately cancel and reinforce each other, known as interference, thus generating a fringe pattern. Just make sure you note this term also. The photoelectric cell detects the direction and speed at which the fringe pattern moves. The change in the pattern moving in one direction or other depends upon which way the laser is being rotated. Faster the rotation, faster the fringe pattern. And then this is converted in the signals which is used by the aircraft systems. So all the difference that is picked up is at this point here. A fringe pattern is observed. So that's what ring laser gyro is. It has a helium neon gas, two anodes, one cathode, two mirrors. One will be used to make micro adjustments. Another is transparent for the absorption by the photocells of the radio light waves sent. Okay. And a dither motor is to prevent lock in an RLG. Sagnac effect is the change in frequency due to the change in length of the lights emitted or the radio signals emitted. What are the limitations? Just lead. One of the limitation is with respect to drift. In the laser gyro system, the drift is because of the internal noise of the system. And the noise is because of the imperfection in mirrors and their coatings. Accuracy can be increased when the length of the optical path. Optical path means the tunnel of the RLG. When the length is increased, accuracy is increased. So when you have a little larger size of RLG, accuracy is increased. So longer the path available, higher the greater the accuracy. Even a small percentage increase in length, small increase in length of your RLG will give me great increase in accuracy. Now, what is lock-in? We get a laser lock whenever rotations are very low RPM, similar to gimbal lock low RPM. We use a piezoelectric dither motor. Piezoelectric is like quartz based. Okay. A dither motor will prevent the laser lock in a lock-in, in a ring laser gyro or an IRS. Trap down simply means that the three laser gyro rate sensor and accelerometers are connected directly to the aircraft chassis. It's a design feature. Okay. What are The principles here, gravity, integration, earth rotation. Remember earth rotation value 15.04 degrees. And Schuler tuning, transport rate, 84.4 minute error cycle are the keywords. Platform alignment for IRS would be true north, latitude should be explained correctly, longitude will be entered correctly, and aircraft should not be moved when the information is being put, and that is to do with the alignment. The platform alignment procedure is also called as establishing the trihedron. Why trihedron? Because ring laser gyro looks like a triangle. It's not just a triangle, but it's like a cube. So in total, it becomes like a trihedron. What are the advantages? Like I said earlier, these are the advantages for IRS. So IRS is an advanced navigation system that gives us a lot of data that is fed to my autopilot, my manual flying, and gives me a lot of information which has become a sort of primary information for navigators. So all your attitude direction indicators and everything else are standby instruments in one way or the other. And they also take in data from the IRS. IRS uses RLG, ring laser gyro. Ring laser gyro important features we have seen. It stabilizes or gives me stable platform mathematically instead of mechanical. Okay, it has whatever features it has, and the frequency variation because of length change, because of movement of the RLG, develops a fringe pattern which mathematically calculated will help me with the required data that I want. It will also have accelerometers, 3 gyros, 3 accelerometers, 3 types of mirrors, Schuler period, Sagnac effect, and couple of points that we have not discussed, gain medium and all, you can just give it a read. That is how lasers work, the full form for laser. Why do we have IRS? In IRS, we have IRU and CDU. IRU will have ring laser gyros and accelerometers and microprocessors. In INS, we have integrating gyro, 3, and we'll have 3 accelerometers, a mechanical gyro, mechanical platform. CDU is also there, and ISS, inertial sensor system, is there in INS. INS is a self-contained unit where once you put initial position of the aircraft, it will be able to analyze the speed and the deviation from that initial position with the help of accelerometers to determine its present position. And it will also help us with important other data, which will help us with ground speed, track error angles, drift angles, and so much. Furthermore, calculations with respect to if I would have fed my required track, my waypoints, then my deviations, my error angles could also be measured and given as an output to the pilot, which could be selected for observation or control on the CDU. So in all, you see everything that you need to do to maintain your aircraft on a required track. If you have a system called INS or IRS, INS older one, modern is IRS. So most probably all aircrafts will have IRS by this time, which you will be flying for airlines. So they will have advantages, quick stabilizing advantages and all. And accuracy is also there. Gravity effect is also not there. So all in all, we get accurate data that is very important navigational data, which in general navigation you have seen. Otherwise, you would be required to do mathematical calculations to find out. You'll need your CX3, you'll need to remember the formulas, keep looking at your clock and everything. But all that hard work that the pilot does can be prevented, and the pilot can just focus on maneuvering and controlling the aircraft, checking important parameters and safety when we have a system like INS or IRS. So IRS has ring laser gyro, which is important for us. And do make sure that you go through the solved questions also. And that's about it. While going through the session, I would recommend that you also give a quick read through the notes, and you can just stop the video and go through the notes on the screen with the highlighted points. So that's a quick session, students. Just make sure this much you have done thoroughly. It will really help you make the most out of your requirement for your understanding for CPL for ring laser gyro, INS, and IRS. Okay. Instead of taking a live session because it's your final day and you might not be available, I thought I'd just make this and send it to you so that you can quickly study and go through it. 1 hour here, 30-minute read. I think your RLG, INS, IRS will be good to go. So even when you're revising, you can just increase the playback speed and just go through this. All the notes are there on the screen as well. And then you can check through your personal notes also. All the best, students, and take care.